Alright, your American Science Mechanical Engineer publication. Design features, performance, characteristics of high traction 3-axle trucks. H.A. Marta, truck underframe design engineer. MEM, ASME, KD Mel, senior project engineer. GS Tomley, magic engineer, electric motor division. GMC LaGrange. As a result, wheel adhesion investigation, a locomotive truck design provided with improved adhesion performance for the development field test and improved the traction was made possible by the ability of the truck to minimize the reduction of axle load rail during operation. The purpose of this paper is to discuss the design feature of high traction 3-axle truck. Truck provides improved adhesion performance, better maintainability compared to the more conventional structure with the diesel electric locomotives. U.S. results predicted. Performance characteristics and laboratory field tests are present compared to more conventional STD flexible type trucks. Contributed by Railroad Transportation Division, American Society of Mechanical Engineers, presented by the ASME IEE Joint Railroad Conference, Jacksonville, Florida, March 14, 15, 1972. Manual received the ASME Headquarters Department 13, 1971. Copies available until the January 1st, 1973. American Society of Mechanical Engineers, United Engineering Center, 345 East 47th Street, New York, New York, 117. Design features, performance characteristics, side traction, 3-wheel axles. Introduction. While the increased demand for the railroad operation for the United States as well for around the world during the past 10 years, the EMD Electric Motor Division has been extensively involved with the development of mechanical electrical component supports for the high performance requirements. To do with this end, significant improvements have been accomplished in a number of areas, including the diesel engine, generators, traction motors, electrical control of the running gear in trucks and or bogies. Considerable electric motor division development and testing has been done with the running gear related with the field's wheel, rail adhesion, cover negotiation mechanics, trucking design. Some of the works have been published ASME, other literature 818. As a result of the adhesion efficiency, 3-axle truck were developed for domestic and export applications. Electric motor division diesel electric locomotives with a high traction 3-axle model HTC was designed to replace. It gives you a footnote. Number 1 would be the numbers in parentheses designated reference at the end of the paper. So, SE type of the locomotive starting with the production in January 1972. Development and background. Initial development, electric motor division, high traction dates well back to early 1960s when an engineer work was done on lightweight export truck design of the locomotive application, more stringent weight and size. High adhesion support, limited wheel loading requirements were among the primary aspects of the consideration. In addition, with the primary purpose of developing a high adhesion efficiency truck, it was considered essential to maintain simplicity of the design for easy maintenance to improve the component integrity of long service life. The first high traction model was the GLC, which referred to the general purpose lightweight with 3-axle truck arrangement. The GLC was made available in 1964 with a multiple gauge applications covering the locomotive weight range from 156,000 to 210,000 pounds. The GLC truck was show the figure 1 high traction 3-axle truck model HTC. The GLC truck was used for 1,500 horsepower GL-22C locomotives of the Angle, Africa in 1966. In 1964, Associated Locomotive Builders Australia became interested in the same truck concept. Electric Motor Division Corporation with the builder developed a high traction truck for a 55,000 pound axle load used in 1966 and 1967. 3,000 horsepower of the GT-26C. 6-axle locomotive for the Australian railroads reported the operating performance of these locomotives in regards to the adhesion varying in currency. Engineering and test work and laboratory field work were done in 1967 and 1968, which investigated way of the transfer between axle wheel rail adhesion. Special 3600 horsepower SD45 locomotives were modified with a higher adhesion efficiency, direction operation compared with the opposite direction. The test result confirmed that improved the weight of transfer of the one direction operation support with a high traffic after the same proportion reduction weight transfer. This was necessary to determine the other variables affecting the traffic effort when nullifying the expected improvement derived from low weight transfer. In the United States, Electric Motor Division previously refrained from introducing high traction work due to the standardized consideration period with the highest priority during the 1960s. Although the aspect is still a very important one, the progressing railroad operating requirements test experience gained in 1966 and 1968 provided the incentive to develop the entry of the HCC truck of the American Railroad, simultaneously second export of the three-axle truck model GHC using the same components. It was developed for multiple gauge application locomotives ranging in weight from 190,000 to 315,000 pounds. The design of HTC and GHC trucks were developed during the later part of the 1960s. Earlier models of the HTC trucks were used on 7 ST-45X experimental locomotives placed in service in 1970. Considerable amount of testing experience have gained on these experimental locomotives since their introduction. Export model GHC truck has been used since 1970. June 1971 of the 5th of the 3.5 foot gauge 2650 horsepower GT26 Amse locomotives built with the Electric Motor Division for the South African Railroad. A slightly modified version of the same truck will also be used with the 80 locomotives built during 1972 with the Argentina Railways. Following sections of this paper will present the design feature for the HGC truck and a summary of the test result comparing the performance of the HTC truck so that the conventional three-axle truck. Alright, figure 2 shows the adhesion efficiency axle load as a function for a traffic effort of 400,000 pound locomotive. Adhesion efficiency 70 to 100, and then you have your lightest axle load by times the 10 to the third pounds. Coefficients of adhesion, track and accuracy to the 10 and third in pounds. Conventional three-axle, high traction three-axle, nominal axle, 400,000 pound locomotives. Locomotive weight transfer. The goal offset of the HGC program was simple to design high reliable truck to improve the traction compatibility would adequately support the 4,200,000 pound locomotive under current operating conditions such as track profile. The HGC design was developed using many of the concept earlier traction export truck during the development of the HGC truck. Every effort was retained the interchangeable with the parts of the domestic truck design to achieve the highest possible with the tractive product capability of the locomotive traction. Most of the design utilized the maximum amount of the available weight of the adhesion when the power was equal to distributed with each of the axle, which is common. The weight of the axle should be kept so nearly equal with the possible. Since for the lightest axle will determine the locomotive with the pulling capacity limited by wheel rail adhesion control for the power still applied individual axle can further affect the adhesion capable ability of the locomotive. However, this does not involve the truck design, therefore will not discuss in this paragraph. A large amount of the weight transfer can occur between the axles and result of the heavy tractive forces. And it shows figure 3 a locomotive tractive effort coefficient adhesion function of the wheel rail function show the cohesion of the coefficiency of the adhesion is locomotive traffic effort over locomotive weight. Show the traffic effort in 10 to the third pounds by weight and rail friction with the curves based on 400,000 pound locomotive conventional 3 truck high traction axle truck. Figure 2, when accelerating, the stop of the automatic will lift off of the front wheels or distributing part of the weight with the rear wheel. This is also true of the locomotive with the 3 major differences. In the locomotive, the driving axle will get later with the power and wheel, but therefore tend to slip. 2, significant weight transfer usually takes place from only a short time in the automobile for a time in an automobile. However, the locomotive with operation extended periods of time, the high traffic effort, such conditions occur during acceleration grade operation. 3, since there are more than 2 reaction points with such as 2-axle automobile, the resultant distribution weight transfer between the axle depends on the truck geometry, not merely with the unloading and loading of the leading of the traction trailing axles. The phenomenon of weight transfer occurs during both the driving and braking. Predicting adhesion capability of the ability of the truck to minimize the weight of the transfer of the traction measurement in terms of the adhesion efficiency, with the efficiency being equal to the ratio minimum axle load from the specific traffic effort to the normal static axle load. Figure 4 shows the typical locomotive operation. Sand conditions will raise the band by 50%, wet and oily conditions will be lowered by 50%, traffic effort in 10 to the third by pounds, and then goes up from 0 to 140. And adhesion coefficiencies Rise is in 500ths. Adhesion limited to adhesion limited to horsepower, limited to range available. Adhesion are typical dry rail condition, typical horsepower curve, and by 10 millimeter speed. Calculation has shown that the adhesive capacity of the HEC truck would be 15 to 20% greater than the existing six-wheel design used domestically. For example, the figure 2 showed that the SC truck was similar to adhesion performance existing design offered 77% efficiency, while the HEC truck provided with a 93 efficiency with a 25 for adhesion demand. Thus, 400,000 pounds of a locomotive light axle SC truck would be 51,000 pounds compared to 61,000 pounds with the HEC truck. And it's the essence of the locomotive pulling with a drawbar of 100,000 pounds or 25% of the adhesion will require the coefficient friction between the wheel and the rail at 32 hundredths if equipped with SC type truck with the only 27 hundredths. If equipped with the HCC truck, it is apparent that the conventional type of the truck would require 21% high traction efficiency at the wheel rate interface of the new truck with a prevent wheel slip on with the heavy drawbar loads. Figure 3 shows the given value of the wheel rail friction. HCC truck can be pulled greater loads before slipping in the previous design. For example, 2,500 available friction level, the HCC would pull with 93,000 pounds before slipping, while the older SC would pull only 81,000 locomotive operating under normal running. Conditions will encounter varying levels of the traffic effort. Demand maximum locomotive traffic effort will be limited to the horsepower capacity available to wheel the rail adhesion shown in figure 4. Traffic effort versus speed curve of the high horsepower locomotive that had been drawn with a band of the representative of the range of the available adhesion track will support with under dry, unsanded rail condition. Upper limit of typical adhesion level that's sustained with a slightly contaminated track with a good rail with joint with the lower limited representative of the available adhesion moderate contaminated track with bore rail joints that are available. The coefficient adhesion between wheel and rail isn't functioning such that the thing is atmospheric condition, track contamination, rare irregularities. This band will shift as indicated in figure 4. For conditions given in figure 4, speed with below 15 miles an hour, usable traffic effort, adhesion limited to the locomotive, so that the locomotive can develop more horsepower than the rail can support. However, at speeds of 25 miles an hour under limited traction effort, is horsepower limited because the locomotive cannot develop the horsepower that the rail can support. By trimming the speed of the gray area where the locomotive is adhesion and horsepower limited, depending on the given wheel, the real conditions, order of the properly evaluated adhesion capability of the truck. The testing must be done with adhesion limited to areas, if not only cooperative, comparative to locomotive horsepowers can be measured. Alright, figure 5 show the half section of the ACC, conventional 3-axle truck showing major differences. A, motor orientation. B, center plate diameter. C, boiler suspension. Show the conventional 3-axle truck, the coil, boiler spring, the center plate, your traction motor orientation, your high traction 3-axle truck, and your rubber bolster springs. Design feature of the HCC was designed for the maximum performance under the extreme driving and braking conditions of specific truck geometry with the component and orientation suspension characteristics to reduce weight and transfer between axles, accomplished by providing good riding qualities, overall simplicity of the truck arrangements, ease of the maintenance. Minimal weight transfer between axles provides improved adhesion capability of the new truck was achieved by using the following concepts in figure 5. 1. Relative stiff secondary suspension between the bolster and truck frame of the shelf spring with the primary suspension between the truck frame and the journal box. Secondary suspension over 10 times stiffer than the primary, which tends to transmit a large portion of the moment, the reaction of the driving force of the car body rather than of the wheels. A large diameter cell between the truck bolster car body underframe with except a large tractive effort reactions which result with a high traction design, traction motor orientation one direction with each motor resisting in a separate truck frame transom. This allows similar torque reactions for the edge of the axle, promote equal axle loads. 4. Lowering driving space for the contact with the trailing interface between the truck and bolster, provide an increased adhesive stability. Alright, ease of maintenance. It's important to strive for the accomplishment with a high adhesion efficiency with the design and simplicity with the new truck with the essential when they justify adoption of the new design of the domestic applications over the foreign design, usually the traction bar between the truck and the car body, axle with the interconnected by the gears. These arrangements are cumbersome with a maintain more expensive build. Effort has been made to extend the surface of the time with the requirements for all of the truck components and parts for the other expected to provide surface for the life of the locomotive. One of the HEC with the prototype type locomotive was completely dismantled after 1 year service with 114,000 miles into the inspection of the possible problem areas such as abnormal wear, stress, fatigue, deterioration of any kind. The truck was found to be in very good condition. Suspension. Journal oil coil spring provides all for the primary suspension locomotive sprung mass, which result with the good riding quality. The coil steel springs offer improved equalization compared with the suspension for previous 3 e-axle truck. The result of a 38% higher static deflection with a nominal wheel load. The new journal springs will produce a smaller wheel load variation, greater vertical rail irregularity, which helps reduce the wheel slip. As a result of the minimized loading of the truck component with the new rubber springs used to the 4 locations between the truck frame and the bolus to perform a vital role in the high adhesion design. Figure 6 shows the journal spring assembly with the wheel wear shim and a hydraulic shock absorber, and show the primary suspension system. These springs have undergone extensive development in the program of laboratory actual field service. The secondary suspension provides about 5/8 of an inch static vertical deflection, allows for 1 1/4 inch lateral deflection between car body and truck frame. Rubber pads isolate with the truck and track noise. They also serve as a secondary damping medium in the suspension system. Primary damping is provided with a hydraulic shock absorber, which is located between the journal bearing and the truck frame. At both ends, each center axle of figure 6 with a simple rugged adapter bolts with the center of the journal box to accept with the lower mounting pin of shock absorber. The total shock absorber the bolt with the center of the journal with a spring pocket with a primary damping system is designed to control the undesirable resonant motions such as bounce, body pitch, and roll. The shock absorber to maintain the stable conformability ride with a safe operation at all speeds. Wheels. The standard tapered contour cast wrought steel 2.5-inch rim multiple wear wheels are based on truck. Cylindrical contours available recommended with a high-speed operation between above 95 miles an hour. The HEC truck has been designed to accept special 42-inch wheels, which in presently undergoing field evaluation provisions made with the maintained same car body coupler height with any wheel size with the main result of the wheel wear. Shimming can be made with the journal suspension area to accomplish the feature. Figure 6, the lack of the purpose of the shimming compensate for the wheel and can result with the unaxle load severe enough to completely overshadow the high adhesion feature of this truck. It should be noted that similar adhesion losses will occur with the existing truck design when wheels are mismatched. Brake rigging. With one simple exemption, brake rigging with the HEC truck is identical to the SE 3-axle truck, with a handbrake is located at the outside of the truck frame, left side with the number 3 axle refer than the inside of the truck, left side with the number 4 axle, single shoe per wheel. Brake rigging using composition brake shoe, screw type slack adjusters as basic class brakes. Pin type slack adjusters are also available. Journal boxes. Many improvements have been incorporated within the tube of the journal box component with the extent of the shift of the period with the rear cover to provide with the improved labyrinth seal with the extent of the intervals between the notice. Necessary oil addition to 3 times the compared with the older boxes. The new oil filler with oil cup shortens for the time required with the inspect to maintain the oil level, and the no tools are necessary for its removal. The replacement with the journal box supporting has been modified, provide improved with the support with the wear plate, the high strength bolts. Special lock wires have eliminated with the need for the 4 lock wiring, both front and rear cover bolts. Modified front retainer ring provides improved oil flow with the thrust block bearing surface crown rollers, reduce the contact stress between the rollers and the races, thereby extending the surface life of this. Is also improved with a non-sticking rear cover gasket. Your truck frame strength. Structurally, the truck frame and the bolster casting has been designed to adequately support 420,000 pounds of locomotive unlimited surface with maximum drive in the brake condition. Negotiated joint and track with a vertical load rail profile of 3 inches, 1 rail length. The static stress test has been performed in the laboratory. Dynamic stress tests have been run under actual surface conditions, which have been confirmed with the design criteria have been met. Or a locomotive application consideration 3-axle high adhesion truck, which will not interchange with any of the previous 3-axle truck assembly, primarily due to the following differences between the truck: 1 traction motor, air duct location, 2 center plate diameter, 3 carrier body, 2 truck safety interlocking system, 4 overall truck dimension. Truck weight in the truck assembly will weigh 54,600 pounds with a single shoe brakes with a hollow bolster, casting of 60,300 pounds. For glass brakes, the solid bolster of the brake frame with a casting weighs approximately 11,400 pounds. The bolster is 4,500 pounds if hollow, or 82,000 pounds if solid. New truck assembly can weigh up to 15,000 pounds or more than older assembly. Truck dimension wheelbase overlays 163 and 3/8 of an inch. Axle 1 and 2 spacing 79 inch. Axle 2 and 3 spacing 83 and 3/4 of an inch. Truck casting overall length of 19 foot and 1/8 of an inch squared. Overall width of 8 foot and 4 3/4 of an inch. Overall height 37 1/4 inches. Locomotive application consideration. Truck assembly overall length 19 foot 3 and 5/8 of an inch. Overall width 9 foot and 8 and 5/8 of an inch. Overall height 50 and 5/8 of an inch. Alright, note that 2 single no-show brake design added with the 7 3/4 inch glass brake. Note 3 distance show of the standard guide to the transom, adding 10 inches from the class of the brake assembly. 4 add 5 inches outside handbrake crossing over lever, and 5 height shown on the top of the bolster. 1/2 variable supply, adding 3/8 of an inch when standing free. Alright, laboratory and field weight transfer items. In July 1970, the prototype of 3 ST45X locomotive built with the ATC truck with available experimental work with a 6-axle diesel electric locomotive rated at 4,200 horsepower, weighing 3,980 horsepower, slightly more than 66,000 pounds per axle. In order to determine the increased adhesive capacity of the ATC truck series, the laboratory and field tests were conducted of those units with a static weight transfer test that performed with the Electric Motor Division Eastern Railroad early 1971. 18 adhesion tests comparing with the ATC truck to the conventional ST truck was completed with the Midwestern Railroad. The results of the test confirmed the practical value of the high adhesion design concept, in which term led to the adoption of the ATC truck in 1972 for the ST model locomotive. Figure 7 shows experimental weight transfer of the leading and trailing axle of the HCC truck summarized of the Electric Motor Division field test. Axle weight transfer in 10 to the third pounds, and then tractive effort in 10 to the third pounds. Circles EMD X is Eastern Railroad. Locomotive weight of 100,000 pounds. The initial testing HCC truck took the belief of the Electric Motor Division, establishing a relationship between the weight transfer for each of the axle tractive effort of the locomotive was accomplished recording the following quantities: 1, changing the wheel load; 2, the generator current. Tractive load cell, where you have the monitor of the individual wheel loads locating the axle of the test directly with the load cell, since the locomotive traffic effort with the function of the main generator current. Current was measured placing a shunt in the series of the main generator. The stationary test of the locomotive held in place with the blocks welded into the rail, and an application of the brakes for the truck, which was not to be tested for the traffic effort, increased with the change of the wheel loads. Resultant axle loads were recorded with the oscillograph under the conditions of all of the locomotive traffic effort of 74,000 pounds, equivalent to the coefficient adhesion of the 1800s, were usually developed before the wheels started to slip. The axle weight transfer was measured both at the forward and reverse direction of the travel. Figure 8, comparison of the experimental calculated axle weight transfer versus locomotive traction effort from the HCC conventional 3-axle wheel loads. Show the lightest axle weight at 10 3rd pounds from 54 to 66, nominal axle load at 400,000 pounds. The HCC calculated the 1970 weight of the shift test for the ATC truck and the Electric Motor Division Eastern Railroads. In 1967, the weight shift test for the SD truck and the AMD. And the STD calculated in traffic effort over the pounds and thirds, and that's ranging from 0 to 100 and whatever. The static weight transfer for the test was also run with the Eastern Railroad. As probably the first row of the test, the ST45X locomotive, the unit with a taken electronic scale where individual axle weights could measured. Again, traffic extra with determining the function of the main generator current of the locomotive cell with the stationary braking with the remaining units for the consist. As previously tested, the no braking was applied with the truck being tested. The total weight axle load recorded for each axle within the locomotive being powered both in forward and reverse direction. Throttle position 2, 3, and 4. Maximum locomotive traffic effort 70,500 pounds was developed before the braking force consists of overcome the locomotive start of the way. The result of the locomotive with the field of the weight transfer of the summarized in Figure 7 to develop the data points per percent and the change in the axle load and absolute value for each end. For the end axles number 1 and number 6, in either the forward reverse direction function traffic effort, axle N was chosen since it exhibited a large change of the axle load and adhesive capacity of the locomotive related, and the littlest axle since the scatter of the data was between 2,000 and 3,000 pounds, 3 to 4% of the nominal axle load, or 66,000 pounds, but the accuracy repeatable result was considered very good. The calculated experimental weight of the transfer of the curve of the conventional SC truck with the HEC are shown in Figure 8. The experimental data completely compared closely with the calculated weight transfer of both the HEC and the SC trucks at 60,000 pound tractive effort. The measured weight of the transfer was 1.9% greater than the calculated with the HEC truck and 3.1% greater for the SC truck. The increase was due to the friction development between the drum box and the pedestal liners, which presumably greater for the degree of the stack test under actual dynamic operation condition. The improved performance of the ATC truck was made evident the difference of the weight transfer between the two trucks. Thus, any of the given transfer effort, HTC truck effectively produced the high adhesion weight of the locomotive. This means that the locomotive of the ATC truck can deliver the same traffic effort at a lower locomotive weight. Conversely, with the same locomotive weight, with the HTC truck requires a lower available coefficient friction between the wheel and the rail, maintaining given the traffic effort and result in a lower slip risk. Adhesion Test. The development of the data with the efficiency of the ATC truck adhesion test was performed with the Midwestern Railroad to compare the SC-45 locomotive. The SC-45 locomotive simulated operation condition. SC-45 locomotive with the same unit that had been during the adhesion test conducted in 1967 and weighed 397,000 pounds, virtually with the same weight as the SC-45X. The SC-45 6-axle diesel electric locomotive related to the 36,600 RPMs equipped with the conventional SC truck. Both of the units have thoroughly checked to ensure that they were operating properly with reducing the rate of the horsepower. A consist compared with the two SC locomotive of the electric motor division test car with the two dynamic brake operated with the test train with the two different test sites. So the first location obtained with the level of the tangent track with the primarily welded to the rail. Secondary test site efficiency, different degree with the curve of construction of the joint rail. Since the purpose of the test was to verify and improve the performance of ATC trucks, the primary objective was to maintain similar operation conditions between the two locomotives. Especially available the coefficient for the friction between the wheel and the rail. Therefore, numerous tests were run made over the same section of the track. Each unit attempts to be made to conduct the test each for the locomotive within a few hours to minimize variation on the rail. Surface to do with such things such as weather condition, time of the day, passing of the train. For example, the passing of the train could cause the track to become oily, and with a 50% level to be able the friction would be a result. The remainder of the consists of the provided with the dynamic braking load simulating with the train load with the unit of the power of the braking load was controlled with the test card, adjusting according with the test condition. Hump control, variable throttle control was installed on each of the locomotives so the maximum traffic effort could be applied with the wheels at all times. Initial with the testing conducted with the wheel slip protection. However, it was found that the wheel slip occurred too frequently and will overslip to increase with beyond control, mainly regulating with the power was too slow, therefore preventing damage of the traction motor wheel with the wheel slip were used. Both units were equipped with a similar IDAC wheel slip system, and the automatic application same with the IDA system was deliberately prevented. Alright, by combining with the IDAC with the variable throttle control with the possibility to operate with the maximum throttle tractive effort. Variable throttle control could be established level of tractive effort about with the IDAC. Could modulate with the maximum traffic effort was obtained with increase the power of the motors until the small wheel slips occur, but at this point with the IDAC, reduce the power by watching traction motor amperage if possible to determine the frequency and the magnitude of the production. After the slip of the corrected, small amount of additional power were applied with the traction motors until it was obvious that the IDAC was continuously operating when the maximum traffic level had been reached. Numerous tests were run with a locomotive under varying operation conditions. One stop at 18 miles an hour. Pull dynamic brake with the air brakes were applied with the load unit Powers would gradually apply with the test unit with the preventing the gross slipping to get the test of the train moving the variable throttle with the control of the being operated to make obtain maximum traffic effort. The braking force was slowly reduced to build up the speed with its consist to the 18 mile an hour to 2 mile an hour while consistent travel. The 18 mile an hour test locomotive with the maximum throttle. The dynamic braking was slowly applied to decrease the train with once under 10 miles an hour. The air brake was used to bring with the consist down to 2 miles an hour with reducing speed with the variable throttle. The control was adjusted, maintain maximum power of the wheels without gross slip. Figure 9 shows the tractive effort in time to the third time pounds at 70 to 120 pounds. Adhesion 20 to 25 and 30. Your high truck and tractional truck, conventional truck. The test data with the welded tangent truck recorded on March 11th, 1971, between 4 o'clock and 4:15. They show the time in seconds. Alright, 3. The constant speed of 5, 10, and 15 miles an hour with the throttle control, the maximum level of the traffic effort, the gross slipping correction of the braking load with adjusting maintained with the constant speed. With the data was recorded. The XY plier located the electric motor division test car, the fully equipped with the mobile laboratory contained with the modern data acquisition record instrument. First 2 testing procedure resulted in traffic effort, various speed curve of the last will proceed to provide with the traffic effort. The version of the time supply with the known constant speed with since one end of the test car has been calibrated. Drawbar with the traffic effort of the ST46. 45X must be directly with the drawbar pull, as well from the main generator current with the traffic effort of the ST45 with the term of the main generator current with the individual axle speed with the ST45X. Train speed with traffic profile was recorded with each of the tests was run with the oscillator wrecker. Figure 10 shows the axle load distribution of 400,000 pound locomotive and 25% traffic effort. It shows the high traction 3-axle, conventional 3-axle, and the nominal load of 66,000 pounds and 100,000 pound locomotive traffic effort. Table 1 and some of the result obtained with the table and tangent track. The level of the maximum available efficiency for the fraction and low over the dry welded area. We're at welded rail. However, it may have been slightly contaminated relative to the value of the adhesion between the ST45X and ST45 may be considered the typical operation, which both the locomotives were limited adhesion but not yet rated horsepower. The HCC constantly provided 12 to 44% higher adhesion than the SC truck, with it confirmed with the theoretical calculation shown figure 3. At 8 miles an hour, the ST45X developed 83,000 pounds of traffic effort, and this while ST45 confirmed to deliver the 74,000 pound with a representative 12% increase with the drawball Pearly. Another condition with the conventional 3-axle truck delivered 74,000 pound traffic after with a predicted value of the HTC truck 83,800 at 13% increase over the drawball Pearly. Table 1 shows the summary adhesion limited to test data under the dry welded rail condition of the tangent track, the ST45X with the HTC truck, and the SC45 with conventional truck, and it showed the number of miles per hour, 8, 10, 12, 14, and 16. Traffic effort of the SC45X and adhesion coefficient percentage, and the SC45 conventional truck traffic effort in pounds and over the adhesion coefficients percentage. Alright, sample the actual test data of the traffic effort result of the potential speed with 5 miles an hour shown figure 9. Available adhesion during the test run with a very high test result with above 70 miles an hour would have been effective with the horsepower limitation. However, 5 miles an hour, both locomotives could deliver the horsepower necessary to develop the maximum traffic effort, and then the rail could support. The HTC truck provided 16% greater tractive effort than a conventional truck. The test result was confirmed with the validity of the theoretical calculation. Predicted increase of the adhesion compatibility. One method of checking with the test result was going to be made in figure 2. Conventional truck developing 93,000 pound traffic effort with required with a coefficient friction in between the wheel rail 2900 and 180% of the traffic effort at HTC requires a efficiency friction of 2900. Thus, both of the trucks were developing inspected traffic effort for the given track condition. Conclusion. It has been shown that the HTC truck offers improved adhesion capability over the more conventional SD flex coil truck of the domestic 3-axle truck. The calculation field evaluations have shown the improvement in the range of the 10 to 20% of the means of the locomotive of the HTC truck, whereas the low efficiency with the friction rail needs less than the total locomotive weight produces the same traffic ever the previous 3-axle of the truck. But this means that slip risk of the locomotive equipped with a high traction choke should be lower than the locomotive having the same weight value of the conventional design. Additional benefit of low weight with the train for the lower maximum axle load rails during the operation tractive effort. Figure 10. Furthermore, soft primary suspension provides reduced wheel rail load variation and lower twisting mounts. Truck casting during operation aspects are significant and therefore offer improved reliability performance on a present commonly encountered track conditions. Acknowledgement. The experimental data represented in the article result of the test conducted with the cooperation of the customer, railroads in the field, electric motor division, experimental test, instrumentation, field engineering section. The authors also wish to express the appreciation of L. Buckholtz and his group of the preparation of the illustration and the L.F. Koshi for continued advice and encouragement and support with this work, and ensure the references. And this was an ASME publication of the design feature performance characteristics high traction 3-axle truck.